can have a left child and a right child, and that's it. Um, and so we'll see how this is very similar to what we did yesterday, but just slightly different. So we're in the binary tree class. It has one instance variable, which is a reference to the root node, just like for our tree class yesterday. The first method we have here is the constructor, the default constructor. I added documentation that we want this to construct an empty tree. So how do we represent an empty tree? An empty tree will be a tree that has no root. So we'll say this dot root equals null. That's how we'll represent an empty tree. Um, However, we probably want a tree that actually has some data in it. So this constructor, so you're going to see we're going to have a more sophisticated set of constructors for today's binary tree than we had for yesterday's generic tree. So this constructor takes one parameter, which is a reference to the data for the root of the tree. So we want to construct a tree with exactly one node and no children, and we're provided the data for that node. So this is going to be very similar to the constructor we wrote yesterday, where we need to make a new node, and then we need to initialize all the instance variables for that node. But I got a little bit ahead of ourselves here. Like we need to actually define the node class first. So let's scroll down to where it says static class node. Similar to yesterday and similar to our linked list node, we do want an instance variable of type object that we'll call data. So that's consistent with what we've done before. Again, this tree, we could make this tree a generic. We're just going to have it, all of the data be of type object instead to keep things a little bit simpler. Um, Yesterday, our second instance variable was a list of references to nodes because we could have an arbitrary number of children. Now that we're in our binary tree, we can have exactly two children. So we can simplify our data structure by having one instance variable of type node, and we name that left, and another instance variable of type node, which we name right. So the advantage of this binary tree and where we get some performance gains from is we don't have to create new array lists. We don't have to add elements to an array list. We simply always have these two instance variables left and right. If they're null, that means there is no left child or right child. And if they're not null, then that's the reference to the child. So now that we know these are the three instance variables we'll have for a node, we can go back up to this constructor and initialize each of those three reference or instance variables. So data is going to be set to root data because that's what's specified in the constructor. And then we can say this dot root dot left equals null, meaning we have no left child. This dot root dot right equals null, meaning we have no right child. So that's how we encode, or that's how we specify all of this. Our third constructor is a constructor that takes three parameters, a reference to the data for the root of the tree, and then a reference to another binary tree, which will be the left subtree, and a reference to another binary tree, which will be the right subtree. And so this is not much different to do. We're going to say, again, this dot root equals new node. We still need to make a new node for the root of our tree. We still need to initialize that node's instance variables. So this dot root dot data equals root data, just like before. And then this dot root dot left equals, and this dot root dot right equals. Go ahead and complete those two lines of code. You may remember I struggled to write very similar lines of code to this yesterday. So I want to see if you all can do better than that and write correct lines of code for these two lines today. What do we think? What do I put here? How do I finish line 38? Absolutely. So I have to say left dot root because the instance variable left of a node refers to another node. It does not refer to a binary tree. So we can't just say this dot root dot left equals left. We have to say left dot root because we need to refer to the node, not the tree. And this is right dot root. There we go. We're going to take a short detour here because I want to show you like a code clarity and conciseness optimization thing. Makes your code more maintainable. The constructor we just wrote is extremely similar to the constructor we wrote before. It's just that here we said null and here we actually passed in these tree things. This can be a maintenance issue when we have two chunks of code that are so similar, but they're not the same, and we've duplicated that logic. And so, an approach you can take is you can have one constructor call another constructor in Java. And I expect you saw this last year, but probably didn't do it that much. And so, this is the second use of the keyword this. I can replace all of this code here and I can say this, meaning construct this object, the one I'm in the middle of constructing, and then I can pass the three parameters. I can pass root data, and then here, can I do this? No, I can't because I don't have a node. All right, just kidding. That's not going to work. All right, let me show you it in a slightly different way. We could have the third constructor call the second constructor and then just make a couple of changes. So I could delete, I still want to show you the syntax. So we'll make it work this way. I could replace those two lines of code by saying construct this binary tree object, and I could pass root data. And so what line 36 does, if we were stepping through this code in the debugger, line 36 would jump to this constructor. It would make a new node. It would initialize root data. It would set left and right to null. It would come back to this constructor and then change left and right to refer to the roots that it's supposed to. So there we go. Here's how we can use this to like have one constructor call another. All right, so what else we got in here? Let's see. We wrote our node class. We've got a height class. So I'm going to show you a very similar strategy as to what we did when we were doing linked list recursive operations. We're going to do the same thing in a tree. Trees love recursion. We're going to see recursion over and over and over again. So here's our public method, public int height. It's to return the height of this tree. Right now, it just returns 0. We're going to use the static recursive helper method strategy that we used back with our linked list. We can't recurse on this method height because there's no parameter to help us maintain the state from one call to the other. So instead, we create a private static recursive helper method called height that does take a parameter, which is return the height of the subtree whose root is the specified node n here. Okay. So in the public method, just like we did with the linked list class, we simply call the private static helper method. So I could just say height, but to be explicit here, I'm going to do class name dot height. which I can do because it's static. And then I'm going to say this dot root because I want to find the height of the subtree where the subtree is the root of this tree. And then up here, I can implement the recursive algorithm for calculating the height. There's always three parts to recursive algorithm. The first part is our terminating condition, which is the answer to the question, what is the simplest tree to calculate the height of? What do we think? Okay. What's that? An empty tree is the simplest tree to calculate the height of. So that's our terminating condition. If n equals null. So remember, an empty tree is a tree where the node is null, the root is null. We will simply return 0. That's our terminating condition. Else, the second part of recursion is to take one small step towards the solution and then delegate solving the rest of the problem to someone else recursively. The one small step we can take is if we have a non-null node, we know the height of the tree is one more than the height of like the rest of the tree. So I can say return 1 plus, now I have a left child and a right child. I can ask each of them to calculate the height of their respective subtrees, but I don't want to like add them together because that's not what height is, right? Height is how many levels there are. I don't know if my left child or right child is going to have a taller, have a greater height tree. So I can just take the maximum of the two. So I'm going to say 1 plus math.max, and I'm going to recursively say binary tree dot height. Hey, left subtree, calculate your height. And then, hey, right subtree, calculate your height. So I don't really care if the left child or the right child or the left subtree or the right subtree has a greater height. I'll calculate both. I'll take the maximum of those, add 1 to it to count for my height, and return that value. I think recursion fits pretty well with linked lists. And it's not just like a personal opinion, like that's why there's so many practice activities with recursion with linked lists. I think recursion fits extremely well with trees. Trees are like built for recursion. And so you're going to see this pattern over and over again in this chapter. All right, we have a couple accessor methods we need to crank through. So let's do those, and then we can run our code. Is empty returns whether this tree is empty. Return this dot root equals null. If the root is null, the tree is empty. That's our definition. All right, what's the next accessor method? Data. Gets the data at the root of this tree. Oh, that's not too bad. Return this dot root dot data. I think the final two methods are a little bit trickier. Left and right. Gets the left subtree of this tree. Right gets the right subtree of this tree. The return type of this method is a binary tree. Again, this is where like types can be confusing, and very often we want to use like internal types like nodes, but none of these methods actually return a node. So even though we're like, oh, this is easy, this dot root dot left, that's not going to compile, right? Because we're mixing our types. Left is of type node. It is not of type binary tree. So that will not work. Instead, we actually have to make a new binary tree object for the subtree we're going to return. And then we're going to initialize the root of that subtree to this dot root dot left. So there's an extra step there that we have to take to make this work. Go ahead and code the right method as well. So when you're done, I created an example for you to make this a little bit more concrete, something you can run against the code we just wrote. I created the code that corresponds to the slide I shared about the decision tree. So if you click on if you click on decision tree demo, here is a program that has all of the questions you saw on the slide for the different animals encoded. And you'll notice it's kind of weird how we have to build these binary trees, but I did it like this is all one Java statement. And I formatted it in such a way as like kind of in a left to right fashion. I'm trying to represent the nodes and the subtrees and the children and all the things. So try to make a visual connection between the slide and the code here. And then here's the code that actually then will prompt the user, asks the questions, reads the answer, and then navigates through the decision tree. So you can go ahead and click on run. You can answer the questions and then see how it behaves and that it works the way you expect. So I'm going to give you a moment to do that, and then we're going to touch briefly on a little bit of math.